Chapter 3, Section 2, Graphing Rational Functions. So in the previous lesson, we learned how to determine the domain of our rational functions and also the vertical asymptotes of our rational function and the end behavior asymptotes as well. In this section, we're going to go all the way, if you will. We're going to actually graph the rational function by doing everything we did in the previous lesson and more. We're going to actually find the intercepts and gather all the information we can in order to graph these rational functions. Here are some steps that I think might be helpful for you to follow. These are the steps that I'll be following for every single rational function we consider. All right, here goes the first example. We have this rational function, x plus 1 over x squared minus 4. All right, the first thing I'm going to do is factor this polynomial. The numerator doesn't factor, but the denominator does. So the denominator is x plus 2 times x minus 2. Because there are no common factors between the numerator and denominator, I know there is no hole in the graph. Next, I will determine what the vertical asymptotes are. And the way I find my vertical asymptotes, vertical asymptotes. The way I find my vertical asymptotes is by taking the factored form of my denominator and setting it equal to 0 and solving. So you should be able to see that your two vertical asymptotes are x equal to positive 2 and x equal to negative 2. Remember, these are two vertical lines that your graph will get infinitely close to. Now keep this in mind, everybody. Because there are two vertical asymptotes, that means there will be three pieces. It'll split your plane into three pieces. One more time. Because there are two vertical asymptotes, it'll split your graph into three different pieces. For step 3, we want to determine the end behavior asymptote. This requires us to compare the numerator of the denominator and the numerator of the degree of the. Okay, let me say that again. This requires us to compare the degree of the numerator and the degree of the denominator. There we go. The degree of the numerator is 1. The degree of the denominator is 2. Because the numerator has lesser degree than the denominator, I know for sure we will have a horizontal asymptote. Okay, this is my abbreviation for horizontal asymptote. And because the degree of the numerator is less than the degree of the denominator, I know the horizontal asymptote will be y equal to 0. Okay, so basically the x-axis is our horizontal asymptote. Step 4, we want to find the intercepts. Let's find the x-intercepts first. Now, in order to find the x-intercepts, what we want to do is take the numerator only, set it equal to 0, and solve. All right, so here's my numerator, x plus 1 is equal to 0. When I solve this, I get x is negative 1. So the ordered pair for your intercept, your x-intercept, which you only have one x-intercept, is negative 1, comma 0. That's your x-intercept, okay, everybody? And keep in mind, you only have one x-intercept. Now let's find the y-intercept. You always only have one. The way we find our y-intercept is by plugging in 0 for x. So evaluating f of 0. So you're going to have 0 plus 1 over 0 squared minus 4. This turns out to be negative 1/4. So your y-intercept in ordered pair form is 0, comma, negative 1/4. That's your 1 y-intercept. Okay. Now, because the end behavior asymptote is the y-axis, I don't have to determine whether the graph crosses the end behavior asymptote or not. So let's go ahead and show what we have so far. So the first thing I'm going to do is plot my vertical asymptotes here. Remember, these are always, you always use a dashed line to show these because they're not part of the graph, okay? But they help you get the graph. Your vertical asymptotes are x equal to 2 and x equal to -2. They're vertical lines. Now your horizontal asymptote is y equal to 0, namely the x-axis, like that, okay? Now let's go ahead and plot the intercepts. So you found an intercept, an x-intercept at -1, 0. Now keep in mind that lies right on the end behavior asymptote, right? It lies right on the x-axis. Okay, now that is your one and only x-intercept. And then you have a y-intercept at -1/4, which is about right there, okay? All right, this is everything that we've gathered. Now, what we're going to do is remember that there are 3 pieces for this graph. You have a piece over here to the left of this vertical asymptote. You have a piece right here in the middle in between the 2 vertical asymptotes, and a third piece that's to the right of this vertical asymptote. I advise us to work left to right. So let's get this piece over here to the left. We have to determine whether the graph over here to the left of this vertical asymptote is either up here above the x-axis or below the x-axis. Now keep in mind, whichever it is, it has to get infinitely close to your asymptotes, but never touch them. So in order to determine whether it's above the x-axis or below the x-axis, let's plug in a number that is to the left of -2. Any x value to the left of -2 will do. How about -3? Let's plug in -3 in for x and see if whether we're getting a negative output, which will put me below the x-axis, or a positive output, which will put me above the x-axis. All right, I went ahead and plugged in -3, and I got -2/5. That means to the left of -2, I am going to be negative, right? Which is below the x-axis. So I can fill this in. This branch is going to look something like this, everybody. Now notice that to the left here, it's getting infinitely close to the x-axis, which is my end behavior asymptote, but it cannot touch it. And then it's getting infinitely close to the vertical asymptote, again, does not touch it, all right? As far as the middle piece is concerned, I know these 2 points here have to be connected. And from the y-intercept, I know that I have to go downward. I cannot go back upward here, because if I did, I would cross the x-axis again, and that would be an additional x-intercept, which we do not have. To the left of the x-intercept, though, I need to know, do I go up here or do I go down like this? So let's plug in a number between -2 and -1. So let's plug in -1.5 and see if I'm positive or if I'm negative. All right, guys, I plugged in -1.5 into my function. When I do -1.5 plus 1, I know it'll be a negative value. And then when I square -1/2 and then take 4 away, I know that will be negative. And a negative divided by a negative is a positive. So I know that after it hits this x-intercept, it has to come up into the positive area. So it's going to come up after all. So then it has to behave like this, okay? All right, finally, we need the third piece, which is over here. I'm either above the x-axis or below the x-axis. Plug in a value, any value you want that is greater than or to the right of 2. So how about plugging in the number 3? All right, so I plugged in 3 into my function, and I got +4/5. The fact that it's positive tells me that over here, I'm going to be above the x-axis. Something like that. And again, these are sketches, okay, everybody? So please don't feel that you have to be perfect, but we are trying to be, as accurate as possible. So this is the final graph of our function. Notice you have 1, 2, 3 different pieces, okay? 3 pieces only. Here's the next function, 3x minus 4 over 2x plus 1. Now, the first step, remember, is to fully factor. However, the numerator and the denominator are prime polynomials, meaning they don't factor any further than what they are now. So that is kind of, done for you, right? So we can go straight to step number 2, which is let's find the vertical asymptote. Remember, in order to find the vertical asymptote, all we need to do is set the denominator equal to 0 and solve. And so we're finding that the vertical asymptote, there's only one of them, and it is x is equal to -1/2. I'm not sure if you remember this example from the earlier lesson, but anyway, there's only one vertical asymptote, and because there's only one vertical asymptote, that means there's two pieces to the graph, two pieces. All right, let's move to step number 3, which is to find the end behavior asymptote. Now, in order to determine what kind of end behavior asymptote I have, I need to compare the degree of the numerator to the degree of the denominator. Now, the degree in the numerator is 1, the degree of the denominator is 1. Because their degrees are the same, I know I have a horizontal asymptote. And the equation that defines it is y is equal to the leading coefficient of the numerator, which is 3, over the leading coefficient of the denominator, which is 2. So y is equal to 3 halves. This is the ratio of your leading coefficients is always your horizontal asymptote whenever the degrees are the same. All right, let's go to step 4, which is to find your intercepts. Now let's find our x-intercept first. Now it is possible to have more than one x-intercept, okay? The way I find it or them is by taking my numerator only, setting it equal to 0 and solving. So you can see here, hopefully, that once we solve for x, we are getting only one x-intercept, and it is 4/3, comma 0. This is the one and only place at which the graph is touching and crossing the x-axis. Now let's find the y-intercept. Let me move this up a little bit. All right, let's find the y-intercept, okay? Now remember that in order to find the y-intercept, we plug in 0 for x. So in this case, we're doing g of 0 in the original function. All right, so when we plug in 0, it's 3 times 0 minus 4. I'm plugging 0 into the original function right now. 2 times 0 plus 1. Basically, you're getting -4 over +1, which is just -4. So the ordered pair is 0, comma, -4. This is the y-intercept. You always have just one y-intercept, okay? It's possible to have multiple x-intercepts, but you will always only have one y-intercept. Now, because the end behavior asymptote is not the x-axis, I need to determine whether the graph crosses my end behavior asymptote. So now watch this carefully. The way I determine whether the graph crosses my end behavior asymptote is by taking my function, setting it equal to the end behavior asymptote, which we just found to be 3/2. Remember that? In the previous step, we found the end behavior asymptote to be y equal to 3/2. That's why this number is here. Solve this equation to determine whether the graph crosses the end behavior asymptote. Now, what I'm going to do to solve this equation is, and there's multiple things you can do, I'm going to cross multiply. Okay, I'm going to cross multiply. So when I cross multiply, I get 2 times 3x minus 4 must be equal to 3 times 2x plus 1. Okay? And now I will distribute the 2 on the left, and on the right I'll distribute the 3. Okay, everybody? So then we end up with 6x minus 8 is equal to 6x plus 3. Now I can see right away that these 6x's cancel, and I'm left with a contradiction that negative 8 is equivalent to 3. Nope, that's a contradiction. This tells me that the graph will not cross my end behavior asymptote. All right, I think we might have everything we need in order to graph our function. So let's go to the x and y coordinate plane and just plot everything that we just found. All right, let's plot our vertical asymptote, which is x is equal to negative 1/2. So this is x is equal to negative 1/2. This is your vertical asymptote, and there's only one. This right here splits your graph into two pieces, one to the left of the vertical asymptote, the second piece over here to the right of the vertical asymptote. Remember, there's only two pieces. Then the horizontal asymptote is y equal to 3/2, which is y equal to 1.5. The graph will get infinitely close to each of these lines. Now, let's graph or plot our intercepts. Our x-intercept is 4/3, which is a little bit, it's 1 1/3, so a little bit greater than 1, right? About right there. And then the y-intercept is negative 4, which is here. Now, you have to remember that the graph will get infinitely close to these asymptotes, but will not touch or cross either one. But these 2 points here have to connect, and then you have to approach the end behavior asymptote over there, and then down here you have to cross like that. You have to go down that way. Now over here to the left, this would be wrong, everybody. This would be wrong. Watch this. If I do the branch like this would be wrong because this would give me another x-intercept, which we do not have. So instead of it being below the end behavior asymptote, it must be above the end behavior asymptote like that. No need to choose a value from each interval or anything like that. We know by logic that it has to be up here, okay? All right, here's the graph. Here's our next one. H of x is equal to x squared minus 1 over x minus 3. Step number 1 has us fully factoring. Let's see, we can factor the numerator as a difference of 2 squares, and the denominator is already fully factored. All right, good. There are no common factors between the numerator and the denominator, so that lets us know that there will be no holes in the graph. So let's go to step 2, find the vertical asymptotes. Recall that we find the vertical asymptotes by setting the denominator equal to 0 and solving it for x. So we see we only have one vertical asymptote, which then means there's two pieces of the graph. Let's find the end behavior asymptote. All right, let's compare the degree of the numerator to the degree of the denominator. The degree of the numerator is 1 more than the degree of the denominator, degree 2 over degree 1. Whenever the degree of the numerator is 1 more than the degree of the denominator, it will be a slant asymptote. We'll have to use division to find that slant asymptote. Because the divisor is of the form x minus c, we can use synthetic division if we like, right? And so here we go. The coefficients of my numerator are 1, 0, negative 1. Remember, that's leading coefficient 1, 0 for the first degree term that's missing, and negative 1 for the constant term. Remember, I'll take the opposite of what I see, so I'll put positive 3 right here. Okay, everybody? All right, so let's do this. Let's bring down the 1 here. 3 times 1 is 3, 0 plus 3 is 3, 3 times 3 is 9, negative 1 plus 9 is 8. The equation that defines the slant asymptote is y equal to the quotient, which is 1x plus 3. This is the slant asymptote. Okay, so this is a line in slope-intercept form, right? An equation in slope-intercept form. It's a line whose slope is 1 and whose y-intercept is 3. Now let's find our intercepts, x-intercepts and our y-intercept. Okay, the x-intercept, remember you'll find those by taking your numerator and setting it equal to 0. I took the original numerator. I could have taken the factored form of the numerator as well. It's up to you. When I add 1 to the right-hand side and take the square root of both sides, I get plus or minus 1. So you have two x-intercepts. One of them is 1, 0, and the other one is negative 1, 0. So there are two locations at which the graph will cross the x-axis, all right? Now let's find the y-intercept. The y-intercept is always found by substituting 0 in for x. So basically, h of 0. So it'll be 0 squared minus 1 over 0 minus 3. So negative 1 over negative 3 will be positive 1/3. So then it's 0 comma 1/3 as your one and only y-intercept. The last thing that you and I should probably figure out is whether or not the graph will cross the slant asymptote. This will be step 5. So what we do to determine whether there is a point of intersection between the graph and the slant asymptote is we set our whole function equal to the slant asymptote, the end behavior asymptote, which was y is equal to x plus 3. This is the slant asymptote that you and I found a few steps ago. Now, what I'll do is I will solve for x. A little while ago, when we did a problem like this, at this step, what I did was cross multiply. You can still cross multiply if you like, if you just remember that x plus 3 is really over 1. So cross multiplication works like this, okay? And so then you would have 1 times x squared minus 1 must be equal to x minus 3 times x plus 3, which is basically x squared minus 1 is equal to x squared minus 9. After you distribute all of this out, you get x squared minus 9. Notice that x squared and x squared cancel out, leaving you with a contradiction that negative 1 is equal to negative 9. All right, everybody, since it will not cross the slant asymptote, I think we have everything we need now to graph this function. Let's go. All right, let's first plot the one and only vertical asymptote, x equal to 3. Now keep in mind, everybody, this one and only one vertical asymptote splits your graph into two pieces. One piece over here to the left and one piece over here on the right. The slant asymptote has the equation y equal to x plus 3. That means the slant asymptote crosses the y-axis right at 3, and the slope is 1. So up 1 to the right by 1, up 1 to the right by 1, up 1 to the right by 1, and so forth. So the slant asymptote is something like this: down 1 to the left by 1, down 1 to the left by 1, down 1 to the left by 1, something like this, okay? Give or take. So these are your two asymptotes. One of them is vertical, the other one is slant. Now, your x-intercepts, remember you had two of them, 1 and negative 1. Remember that your y-intercept is positive 1/3, which is about right here, kind of hard to show, but a little bit above 0 there, all right? So here we go. That's all we have at the moment. Now, the graph has to go through these 3 points and has to get infinitely close to that slant asymptote and this vertical asymptote. It has no choice but to behave that way. That takes care of the piece that is to the left of the vertical asymptote. Remember, nothing up here, okay? You can't have another one up here. If you did, then you would cross the y-axis, and that would be another y-intercept, and that's impossible because you already found the one and only y-intercept. So the area to the left of the vertical asymptote is done. Now you need the area to the right of the vertical asymptote. Now let me show you what is not happening. This is not happening. Okay, this is not allowed because if it were, then it would cross the x-axis again, and that would produce another x-intercept, which we do not have. We already found the two x-intercepts, 1 and -1. So then the graph on the right side of the vertical asymptote has to be up here, trapped, if you will, between the vertical and the slant asymptote. All right, everybody, this is the final graph. That was a lot of fun. All right, check this out. F of x is equal to 2x plus 6 over x squared minus 9. All right, step number 1, let's factor. So the numerator can be factored by factoring out the GCF, which is 2. And then the denominator is a difference of 2 squares. So it factors as x plus 3 times x minus 3. Now you can see that you do have a common factor. You should divide those out. This will produce a hole in the graph. We have to figure out where the hole is, okay? But before I do that, let me show you how this rational function can now be written as simply 2 over x minus 3, okay? All right, everybody, let's find out where that hole is. What you can do is you can take out that factor that was, you can take the factor that was divided out, x plus 3. You can set it equal to 0 and solve. And you can see that the hole will exist when x is -3. The hole will exist when x is -3. So the hole will be at -3 comma something. In order to figure out the y value for this hole, or where this hole is, let's take this value for x, -3, and plug it in. You can't plug it into this thing here, because if you do, the function will be undefined because it'll give you a 0 down here in the denominator. Plug x equal to -3 into the simplified form here of this function. All right, let's do it right there. So you're going to get f of -3, and I'm using the simplified form here, okay? So you're going to get 2 over -3 minus 3, which is 2 over -6, which is -1/3. So the hole exists at -3 comma -1/3. That's where the hole is. So when you and I get to the very end of this problem and we want to graph this function, we will plot a hole at this location, -3 comma -1/3. Okay, everybody, from step 2 all the way to the end, from this point forward, I want you to focus on this function here. Don't look at the original. Look at this simplified form. It'll be much easier. All right, so here we go. Please focus your attention here. Step number 2, let's find the vertical asymptotes. Don't look at the original, look at this one, vertical asymptotes. All right, we set our denominator equal to 0, and so it's x minus 3 equal to 0, and you solve. So x equal to 3 is your one and only vertical asymptote. That will mean 2 pieces for the graph, 2 pieces. All right, let's go to step 3, end behavior asymptote. Notice that the degree of the numerator is 0 and the degree of the denominator is 1. Whenever the degree of the numerator is less than the degree of the denominator, that means your end behavior asymptote will be horizontal. So you'll have a horizontal asymptote. And in this case, it will be y equal to 0. It's always y equal to 0 whenever the degree of the numerator is less than the degree of the denominator. Don't forget that y equal to 0 is just the equation that defines the x-axis. Okay, let's find our intercepts. To find the x-intercepts, what we should do is take our numerator, which is just 2, and set it equal to 0 and solve. But 2 equal to 0 is a statement that does not make sense. This is not defined. 2 is not 0. 2 is not equivalent to 0. This is a contradiction. What that means is you do not have any x-intercepts. All right, now let's find the y-intercept. Now remember, the y-intercept is always found by plugging in 0 for x. All right, so I'm going to do f of 0. Now the numerator is fixed at 2. The denominator would be 0 minus 3, so this would be negative 2/3. So the y-intercept is 0, comma, negative 2/3. That's the one and only y-intercept. Now, I don't need step 5, which is determine whether the graph crosses the end behavior asymptote. I don't need that step here because the end behavior asymptote happens to be the x-axis, y equal to 0. And we already determined that it never touches the x-axis because there are no x-intercepts. All right, let's go to the graph. All right, so let's get our vertical asymptote up here. So x equal to 3 is our one and only vertical asymptote, splitting our graph into 2 pieces. The other asymptote is horizontal, and it's going right through the x-axis. So it's y equal to 0, okay? All right, everybody, there are no x-intercepts. Your one and only y-intercept is negative 2/3, so about right there. All right, we know that the graph will never cross your horizontal asymptote, but it must get infinitely close to your vertical asymptote and infinitely close to the end behavior asymptote. I'm pausing for a second because I don't know if you remember, but you and I determined that there is a hole in the graph at negative 3, comma, negative 1/3. So about right there, there's a hole in the graph, and you must show that, all right? So it's approaching there, there's a hole, and then it continues. Now this hole in the graph means that the function is undefined at that location. It's undefined. Now over here, we have to determine whether the graph is positive, meaning above the x-axis, or if the graph is negative, meaning below the x-axis. So we're going to have to plug in a value that is greater than 3. So how about we do 4, okay? Plug in the number 4 into your function, determine are you getting something positive or something negative. All right, I plugged in the number 4, and I get 2 over 4 minus 3, which is just 2 over 1, which at the end of the day, it's positive. So that tells me that the graph over here must be above the x-axis. All right, so there's the other branch. All right, everybody, this is the final picture, the final graph for our function. That was a lot of fun. All right, everybody, here's a brand new function for us named p. Let's go for step number 1, which is factor. Now, the numerator can be factoring out of 4, leaving you with a difference of 2 squares, and the denominator factors as x plus 4 times x minus 2. We should continue factoring here. The numerator can be factored as a difference of 2 squares. So there, that's fully factored. And the denominator is x plus 4 times x minus 2. You can see there are no common factors to divide out. Therefore, there are no holes in the graph. All right, let's go to step 2, vertical asymptotes. Let me take my denominator, and I'm going to take the factored form of the denominator, okay? And let me set that equal to 0, and then solve. And so when you set each factor equal to 0 and solve, you get 2 different vertical asymptotes. One of them is x equal to negative 4, and the other one is x equal to positive 2. So you have 2 vertical asymptotes, which means you'll have 3 pieces of the graph. Now let's move to the end behavior asymptote. Step 3. We must compare the degree of the numerator to the degree of the denominator. Notice that the degrees are the same. Whenever the degrees are the same, you have a horizontal asymptote. Okay? Now, the equation that defines this horizontal asymptote is y is equal to the leading coefficient of the numerator, which is 4, over the leading coefficient of the denominator, which is 1. So it's 4 over 1. That's the same thing as saying the horizontal asymptote is simply y is 4. Okay, everybody? The horizontal asymptote is always y equal to the leading coefficient of the numerator over the leading coefficient of the denominator whenever the degrees are the same. All right, let's go to step 4, which is find the intercepts. In order to find the x-intercepts, take your numerator and set it equal to 0. It'll be easier if you take the factored form of your numerator and set it equal to 0. I'll take every variable factor and set it equal to 0 and solve so that you can see we disregard the constant factor 4, right? We won't set that equal to 0, but we will set these other two equal to 0. And notice that you have two x-intercepts, -1, 0, and +1, 0. Okay? That's supposed to be a comma there. All right, so then 2 x-intercepts. Now let's find the y-intercept. The y-intercept can always be found by substituting in 0 for x. And in this case, when you substitute 0 in for x, I think it'll be easiest, guys, if we plug in 0 in the original. We can do that because there are no common factors here. So when you plug in 0, all you're left with is all these variable terms go away. You're left with -4 over -8. So P of 0 would give me -4 over -8, which simplifies to +1/2. So the y-intercept is 0, comma 1/2. Okay? So these are all of your intercepts. Now, we have to determine whether the graph will cross this end behavior asymptote. Will the graph ever cross this horizontal line? We can answer that question. This is step 5. We can answer that question by taking your function, setting it equal to the end behavior asymptote, and solving. So I'm deciding to take the original function, and I'm going to, I think it'll just be easier if we take the original in this case, set it equal to my end behavior asymptote, which is y equal to 4. Now, remember that 4 is really over 1 if you'd like, and you can cross multiply. All right? So, what you end up getting is 1 times 4x squared minus 4 is equal to 4 times x squared plus 2x minus 8. So the left-hand side is just 4x squared minus 4, but the right, after you distribute the 4, you get 4x squared plus 8x minus 32. Now the squared terms cancel, 4x squared and 4x squared, and you're left with a linear equation. So because of that, I am going to isolate the variable by adding 32 to both sides. This will isolate my variable expression, so I'm going to end up getting 28 is equal to 8x. I will now divide both sides by 8 to get x is equal to, let me move the screen up here, x is equal to 28 over 8. If you divide by 4 here in the numerator and denominator, 4 is the GCF. 4 goes into 28 7 times. 4 goes into 8 2 times. So it'll be 7 halves is equal to x. So you just determined that the graph will cross the end behavior asymptote we're at? Well, at 7/2, comma 4. Don't forget that this is the y value that you used earlier, right? It's actually right there. Remember, the end behavior asymptote is y equal to 4. So this is the point at which the graph crosses your end behavior asymptote. Don't forget that 7/2 is the same thing as 3.5. So if you need to, or if you want to, you can rewrite this as 3.5 or 3.5 comma 4. Okay, that's the point at which the graph crosses the horizontal asymptote. Okay, I think we have everything we need. Let's now go to the x and y coordinate plane and graph this function. Okay, one of your vertical asymptotes was x equal to -4. That's that one. The other one is x equal to 2. Let's plot those. The horizontal asymptote, the end behavior asymptote, is y equal to 4. All right. Now, your intercepts are, x-intercepts are 1 and -1. Your y-intercept is positive 1/2. So that's what you have there. Now, you also have another point, the point at which the graph crosses the horizontal asymptote. And we just figured that out. It was 3.5 comma 4. So I'm going to go ahead and plot that now. Here's 3. So 3.5 is a little bit more, comma 4, right on that horizontal asymptote there, maybe about right there. Okay, everybody? This is the point at which it's crossing the horizontal asymptote. The coordinates there are 3.5 comma 4, or 7/2 comma 4. Now, going left to right, the piece over here it must be up here, because if it were down here, it would create another x-intercept, which you and I do not have. For the middle piece, it has to go through these 3 points and then go infinitely low here, like that, okay? And then for this piece up here, it cannot go through this point and then go down like that, because again, that would produce another x-intercept, which you and I do not have. So instead, the graph crosses and then stays really close to the asymptote. Really, it crosses right here, but then it stays really, really, really close to the horizontal asymptote. All right, everybody, that was really, really cool. All right, everybody, we're almost done. So we have 2 more examples left, this one and one more. This is x cubed minus 8 over x squared plus x minus 2. All right, first things first, let's factor. The numerator is a difference of 2 perfect cubes. If you need a reminder of how to factor a difference of 2 cubes, you may need to look that up or reach out to me, right? Reach out to me, I could show you how to factor a difference or a sum of 2 cubes. I would love to show you that. But it factors like this. All right? And then the denominator factors as x plus 2 times x minus 1. All right, you can see there are no common factors. I'm looking at this 4 right here. I want to make sure that you understand that's a 4. It was a little sloppy. Let me make that better. There, better. All right, there are no common factors here, so there are no holes in the graph. Let's go to step 2, vertical asymptotes. To find the vertical asymptotes, take your denominator and set it equal to 0 and solve. Now, it'll be easier for us if we use the factored form of the denominator. I'm setting each of my variable factors equal to 0 and solving, and you get 2 vertical asymptotes, which means you'll have 3 pieces of your graph. Let's go to the end behavior asymptote. Now I notice that the degree of the numerator, which is 3, is 1 more than the degree of the denominator, which is 2. Whenever that happens, that means I have a slant asymptote. And I'm going to have to find that slant asymptote using long division here because of how this divisor is. It's quadratic. So I'm going to have to use long division to find the slant asymptote. All right, the numerator is x cubed. Let me move that over for us. Sorry. Over here, x cubed plus 0x squared plus 0x and then minus 8. And then the denominator is x squared plus x minus 2. All right, so x squared times x gives me x cubed. So I'll put an x up there. Now it's time to multiply all of my divisor by x, okay? So let's do that. You'll get x squared times x, which is x cubed, x times x, which is x squared, negative 2 times x, which is negative 2x. Now we're going to subtract, and then remember how we distribute and add the opposite. So negative x cubed, negative x squared, positive 2x. This leaves us with negative x squared, positive 2x, and then bring down the minus 8. Now, x squared times negative 1 will give me negative x squared. Multiply all of your divisor by negative 1. You will get negative x squared, negative x, plus 2. Don't forget we are subtracting, and we will add the opposite. So adding positive x squared, positive x, and a negative 2. This leaves you with a remainder of 3x minus 10. Now the slant asymptote is the equation y equal to the quotient, which is x minus 1. That's the equation for the slant asymptote. All right, everybody? This is it right there. All right, so you're disregarding the remainder. All right, let's go to step number 4, which is find your intercepts. Now to find your x-intercepts, we're going to take the numerator and set it equal to 0 and solve. Recall that you always find a y-intercept by substituting in 0 for x. It'll be much easier to go to this form so that you can see every term that has an x. You're going to substitute in a 0, which means they'll all go away, leaving you with just your constants. So then m of 0 will turn out to be negative 8 over negative 2, which is just positive 4. So then your y-intercept is 0, 4. All right, now you and I need to figure out, does the graph of this function cross your end behavior asymptote? Does the graph of this function cross your slant asymptote? That'll be step 5. All right, notice that I set my whole function and I went to the original form of the function and I set it equal to my slant asymptote, and I will solve. Now remember that x minus 1 really has an invisible 1 underneath. You can cross multiply here to solve this for x. Now the left hand side will just be x cubed minus 8 times 1, right? Times that 1, which is still just x cubed minus 8. The right hand side will be x minus 1 times x squared plus x minus 2. Let's distribute the x here, and then we'll distribute the negative 1 there, all right? So the left-hand side is just x cubed minus 8. The right-hand side is x cubed plus x squared minus 2x. That's what I got from distributing x. Now when I distribute a negative 1, I get negative x squared, negative x plus 2. So then, moving this up for us here, that leaves us with x cubed minus 8 is equal to. Now on the right-hand side, I am noticing that these terms are opposite, so they cancel, while these two combine to negative 3x. So on the right-hand side, you have x cubed minus 3x plus 2. Now, notice that x cubed terms cancel, and you're left with a linear equation. So what I'm going to do is I am going to subtract 2 from both sides to isolate my variable. So this is going to be negative 10 is equal to negative 3x. So then finally, just divide both sides by negative 3, and you get that x is equal to positive 10/3. So the point at which it's crossing your slant asymptote is 10/3, comma, wait a minute, how do we find the y-coordinate? Well, the graph is crossing at the slant asymptote. Remember that the slant asymptote has the equation y equal to x minus 1. So if you're looking for your y value, just plug in the x value of 10/3 and you'll get your y value, right? So then this is 10/3 minus 3/3. So your y value that corresponds to 10/3 is just 7/3. That's the full ordered pair for the point at which it's crossing the slant asymptote. Okay. Now, if you prefer decimal form here, this will be 3 and a third for 10/3, right? 3 goes into 10 3 times with 1 left over. So 3 and a third, which is 3.3 with the bar over it, meaning that this 3 never stops, right? It's 3.333333333 and so forth. Here, 3 goes into 7 twice with 1 left over, so it'll be 2.3, 333333333 and so forth, so with a bar. So anyway, I don't know if you prefer to see it that way or not, but this is the point at which the graph is crossing the slant asymptote. All right, let's go to the graph now. All right, remember that the vertical asymptotes are at x equal to negative 2 and positive 1. Get that better. All right, better. This splits, these two vertical asymptotes split your graph into 3 pieces. Now, the slant asymptote is y equal to x minus 1. That means the slant asymptote crosses the y-axis right at negative 1 with a positive 1 slope. Remember, you only have one x-intercept, which is right here. That's the only point at which the graph crosses or touches the x-axis. All right, last example, graph this final rational function. R of x is equal to 2 over x squared plus 3. First things first, let's graph this function. Notice that this cannot be factored, it's just the prime number 2, and neither can the denominator, that cannot be factored. So this is already fully factored, so let's go to step number 2, find the vertical asymptotes. To find the vertical asymptotes, take your denominator, set it equal to 0, and solve. Now there's a problem with this because when we subtract 3 from both sides and then take the square root of both sides, we get imaginary or non-real solutions. So because these are non-real or imaginary solutions, it means you do not have any vertical asymptotes. No vertical asymptotes at all. This is the first function where that has happened. So this is going to be interesting. All right, let's go to step 3, which is the end behavior asymptote. Now, looking at the degree of the numerator, it's 0 because it's a constant term. So degree 0 over degree 2. Whenever the degree of the numerator is less than the degree of the denominator, that means you'll have a horizontal asymptote. And in this case, the horizontal asymptote is y equal to 0, which is the x-axis. So the x-axis is your horizontal asymptote. All right, let's go find the intercepts. To find the x-intercepts, all we need to do is take the numerator, set it equal to 0, and solve. But the numerator is just 2 is equal to 0. There's no solving that. This is a contradiction. So this means there are no x-intercepts. To find the y-intercept, all we need to do is plug in 0 for x. So r of 0. So that'll be 2 over 3, right? Because 0 squared is just 0. 0 plus 3 is 3. Okay, so then the y-intercept is 0, 2/3. All right, everybody, notice so far that we don't have any vertical asymptotes. We don't have any x-intercepts. All right, let's go to the graph and see what's going on. All right, you have a horizontal asymptote right at y equal to 0, which is the x-axis. We know you do not have any x-intercepts. You're not allowed to touch the x-axis. We know that the y-intercept is 2/3. So if this is 1, then 2/3 is about right here. So the graph has to go through 2/3. Now the graph has to go through through that point, and it has to get infinitely close to this one and only asymptote, but it's not allowed to touch it. Therefore, the graph has no choice but to behave like this. Like that. Okay? It's kind of interesting. It looks like a little hill or something, right? So it's getting infinitely close to the asymptote and going through that point on the y-axis. And this is the final graph. It is what it is.